The second type of improper integral involves an infinite discontinuity. So these improper integrals do not have infinity as the lower or upper limit, but the function itself approaches either infinity or negative infinity somewhere within our integration limits. So either at an endpoint or somewhere in between. So we could have an area that converges or diverges. So it might converge to a specific value or it may not. So let's look at an example where we have an infinite discontinuity at an endpoint. So if I want to integrate from 2 to 4 of 1 over x minus 2, you can see I have a vertical asymptote at x equals 2. So I'm trying to find the area there, right? And remember that this function approaches this vertical asymptote but never actually touches it. So this area may diverge, it may just grow to infinity, or it may converge to a specific value. So we're going to try to find that out. So here we are going to replace the limit at which my function, the value at which my function approaches infinity. So it's the 2 that is our infinite discontinuity here, our vertical asymptote. So we're going to change that limit to some variable. I'm going to use c. So I'm going to evaluate this definite integral, and then I'm going to take the limit as c approaches 2. Note here that within this interval I'm going to approach 2 from the positive side. I want to stay within this interval but get closer and closer and closer and closer to the value of 2. So I'm going to approach 2 from the positive side. So I do that antiderivative. I get natural log of x minus 2. Then I substitute 4 and c. I get natural log of 2 minus natural log of c minus 2. And now I take the limit of that as c approaches 2 from the positive. So I have natural log of 2 minus natural log of c minus 2 as c approaches 2 from the positive. Means that this quantity in here is going to approach 0 from the positive. And that means the natural log of a value that's approaching 0 from the positive is going to approach negative infinity. Alright, so now I have natural log of 2, which is just a constant, plus infinity. So I get infinity as my final answer there. So it turns out that this improper integral diverges and doesn't have a value. So what that means is there's an infinite amount of area between this function and the x-axis between 2 and 4. Right? So in this case we had an infinite discontinuity or a vertical asymptote at the endpoint of our integration. And you can see how we approach that. The other type that we might have, we might have an infinite discontinuity at an interior point. So if I have the graph of 1 over x minus 1 to the 2/3, you can see that I have a vertical asymptote at x equals 1. Right? And if I want to find the area between this graph and the x-axis, between x equals 0 and x equals 3, I want to see if there's a finite amount of volume there, or I'm sorry, a finite amount of area there, or if that that area is an infinite amount. So if this definite integral converges to a specific value, or if it diverges to infinity. Right. So again, what I'm going to do here now is I'm going to break up this integral to 0 to 1 and 1 to 3. And so what I've done now is I have two cases where now I'm back to that place where the endpoint is the location of my infinite discontinuity. Right, because the discontinuity occurs at x equals 1. So now I have a discontinuity here at the upper limit of integration, and then this one I have a discontinuity at my lower limit of integration. So I'm going to work on the first one here in this case. So I'm going to create an integral from 0 to c. I'm going to replace the 1 with a c, and I'm going to approach 1 from the negative side. Right? Because as I'm going from 0 to 1, I want to approach 1 from within the interval, so I want to approach it from the negative side here. So I'm going to evaluate this. I'm going to evaluate that definite integral, and then I'll take the limit as c approaches 1 from the negative. So I calculate this definite integral. I substitute c in 0, so I get this expression for the definite integral from 0 to c, and then I apply the limit as c approaches 1 from the negative. So you can see here, as c approaches 1, I'm going to get 0, or I'm going to approach 0 here in this set of parentheses, and so 0 to the 1/3 is 0, times 3 is 0, so the limit is 3. So that part of the area, this part of the area between 0 and 1, converges to 3. Now I'm going to do the exact same thing from 1 to 3, except this time I'm going to replace the lower limit, which is 1, with c, and now I want to approach 1 from the positive side, because I'm in this interval here. Oh, sorry, you can't see that. I'm in this interval here, so I want to approach 1 from the positive side this time. Alright, so again, I evaluate this definite integral. I get 3 times x minus 1 to the 1/3. I substitute the 3 and I substitute the c, and I do the subtraction. And so I have this now. This is, of course, 3 cube root of 2. And as I look at this, I can see as I approach 1, as my c value approaches 1, this value inside the parentheses is going to approach 0. So this entire term disappears. I just have 3 times cube root of 2. So on the left, to the left of 1, I had the area converge to 3. To the right of 1, from 1 to 3, I had the area converge to, to 3 cube root of 2. So the overall definite integral from 0 to 3 is 3 plus 3 cube root of 2.